Good afternoon, everyone. My name is Tyler Thatcher. I am a machine learning engineer for the Acronis SCS MI Lab, which is a part of Acronis SCS, and we are based out of Scottsdale, Arizona in the United States. This video is going to be covering function embedding and software vulnerability in multi-project analysis.
The agenda for today is why do we care about vulnerability, analyzing source code, CVE data collection, the neural network embedding process, additional features, data issues we ran into, machine learning models to score source code, the model's performance, a conclusion, and then a question slide. Why do we care about vulnerabilities? 70% of online fraud is accomplished through mobile platforms. 3 in 5, or 62% of American gamers admit that they worry gaming will become less secure in the future. 53% of people distrust Internet of Things devices to protect their privacy and respectfully handle their information. 34% of United States adults don't trust social media companies at all with safeguarding their personal data. What do all these things have in common that we might be able to address these issues? Source code. Source code could help alleviate these concerns by analyzing the source code for vulnerabilities. Now, what does this mean? This is identifying good and bad code within the source code or programmable code, which is training a model to identify these. Some questions that might have been raised are, how do you identify good and bad source code? What about the cost of data to identify these things? And how do you train a model on source code or programmable languages? Well, how to identify it is we have something called CVEs, which will be covered soon. The cost of data, we use open source data. And for model training, we convert the source code into an embedding or a matrix of numbers that represent the source code. What is a CVE? A CVE stands for Common Vulnerability Exposure. The mission of the CVE program is to identify, define, and catalog publicly disclosed cybersecurity vulnerabilities. There is one CVE record for each vulnerability in the catalog. The vulnerabilities are discovered, then assigned, and published by organizations from around the world that have partnered with the CVE program. These partners then use these CVEs when patching their data, which allows for the collection and analysis of CVEs. The issue, how do we collect the CVE data, and how do we know that a file or a function is a CVE? We chose projects that partner with the CVE program and identify and fix them regularly. The projects we chose are all open source, meaning we can download them from GitHub or version control software like GitHub. The projects we chose are Android, OpenSSL, and Linux. The Android dataset contains 1,137 CVEs and 7,437 functions that are vulnerable within those CVEs. The OpenSSL dataset contains 45 CVEs and 96 functions, which were identified as vulnerable. The Linux dataset contains 1,363 CVEs with 1,994 functions that were identified as vulnerable. You're probably wondering, why are there so many more functions in CVEs? The answer is each CVE does not correspond to one function. A CVE can span across multiple functions, files, and classes in source code. The issue to solve here is, how do we collect them if they can span across the entire code base? We wrote different web scrapers for each project. Each one had to parse every patch that was referenced, grab the commit ID, determine which file it was, and determine which parts are bad code, and then download the file before that commit ID. The example here is from the Android dataset, specifically CVE 2021-0955. The highlighted green code is affixed to the CVE, which makes the red highlighted part of the code the vulnerable code. Now we have identified where these files were fixed. We download the code before the fix, which allows us to have a data set of files that contain the bad code. The good code we can assume is the most recently updated code base on GitHub, as projects patch their projects as CVEs are found. We now have the files of source code. Now we must separate them into functions so we can train machine learning models to identify these good and bad components. This is where SourceML comes in. SourceML is an open source tool that breaks down source code files into tokens in a readable format. The SourceML command line interface is used to convert entire projects from and to source code in the SourceML format. The SourceML format is an XML representation for source code. The XML format allows for querying of the data to achieve the level of granularity required, classes, structs, functions. We chose to analyze on the function level as it seems the most appropriate. This querying can break down any source code datasets that are in file format. We leverage this tool to extract the functions from source code files, which allows us to build a good and bad code at the function level. Now we have the source code broken down to a point of tokens. We now have to convert the data to a readable format for machine learning or statistical models. This is where embeddings come in. To summarize, we take a directory with source code, which we then pass to SourceML to break down to a function level. From there, because there's so much data, we compress the data using byte pair encoding to lessen the data complexity and make training the neural network easier and to improve the performance of said neural network. After the neural network learns the patterns of the compressed source code, it then converts the CSV into an n-dimensional matrix, where each row is a vector that represents the source code of each function. Based on current hardware and datasets, we tested everything from 16 to 512 dimensions, and our team determined that 128 was the most optimal. This most optimal represents a matrix which learns source code patterns like autocomplete on your phone. Once we have finished, we have a CSV file that represents our entire source code repository as a matrix. From this, we generate a few more features which we have found improve the performance of the model. The first one up is the cosine similarity. The cosine similarity is the cosine and the distance to and from each and every other function. So the first function with the cosine of every single function else inside the data set. The second one is the number of CVE tokens. This is, we break down only the CVE files or the bad code files down into tokens. Now, not matrix or numbers, we're talking about programmable source code tokens. So like a for loop, int I. These tokens are then compressed into a set, and we count the number of tokens that are inside this set in every single function of our data set, the good and the bad portion. The length of the function, which is the number of tokens, just like discussed in the previous, of the entire function. The number of parameters, which is just the number of parameters inside of each function. The longest single line of code, or the longest single line of code in each function. After this, we now have a matrix with 133 features. The next problem that we encountered was the amount of CVE functions identified compared to the entire project is very sparse. The chart on the left shows a small amount of data we have to work with. The combined Android, OpenSSL, and Linux kernel, the amount of CVE functions compared to the sum of all these projects was about 1%. To put this into perspective, we found that after we collected 1,676,243 total functions, only 9,527 of them were CVE functions. Since we are trying to identify the vulnerabilities, the CVEs are labeled with a 1 and non-CVEs are labeled as a 0, which means the amount of zeros contained in the multi-project dataset dwarfs the number of positive examples. There is no magic number for positive examples you need to train a model, but 1% is about as sparse as you can get. To remedy this, we turn to upsampling techniques. The upsampling technique that we chose to use is SMOTE, or Synthetic Minority Oversampling Technique. If you'd like to learn more about this, please look it up. It's very common. We just don't want to go into in-depth in this video. But what it does at a high level, it generates synthetic examples similar to clustering or k-nearest neighbor. We took our 1% and we upsampled it anywhere from 5 to 30%, and we found that the most optimal was 15%. Now, what does this mean? This means our total functions went from 1,676,243 to 1,917,152. Specifically, this matters for the CVEs as it went from 9,527 CVEs up to 251,436 CVEs. This means our data set of bad code 15 times, while leaving the non-CVE functions at the same amount, which was 1,665,716. Now that our number of positive labels are not a minuscule amount, we turn to computing a vulnerability score with machine learning models. The four models that we tested are gradient boosting model, a neural network separate from the embedding, a random forest model, and the support vector machine. We found, given our current hardware and time, GBM works the best, or gradient boosting model works the best. What this does is it generates a vulnerability score based on the features we have described in between 0 and 1. The higher the score, the more vulnerable the score is. Anything above a 0.5, we label as vulnerable or bad code. Now that we have a model that can compute a score, let's examine how well this model performed. The metrics that we used was recall was 36%, accuracy was 99%, precision was 30%, specificity was 99%, AUC was 92%, and lift was 74%. Now let's break down what these metrics mean. Recall is a percentage of functions that are predicted as CVEs. This means that for each and every function that we had in the CVE data set, 36% of them were correctly predicted. Accuracy, which is predictions of functions correctly identified as good or bad, was 99%. This is a very high number due to the fact that we only have 15% of our data to be positive. So if it predicts all negatives, the accuracy goes up. Precision is the percentage of positive predictions that are a CVE. Pretty similar to recall, but it's just if a function is a CVE and it was positive, that's what precision is. Precision and recall are generally lower because we have a low amount of data to work with. We're currently working to improve upon this, but they're as good as we can get it for now. Specificity, or the percentage of predicted good code that is not a CVE. Again, this is 99% because, well, we have a lot of negative data. The area under the curve, or how well the model predicts the vulnerabilities, is 92%. Now, generally, this is one of the most favored metrics for looking at how well a model performs, and we're at 92%. It is a little skewed towards the negative results, but 92% is still an admirable score. The lift, or the most important metrics that we go off of, is the number of positive tags predicted in the top X% of data. In this case, we use 5%, so it would be the number of positive tags predicted in the top 5% of our data. That means in the top 5% sorted by score in our data, 74% of them were CVEs. This means that the models that were rated the top, CVEs were among the best in the top 5%. That is a really good thing to happen, meaning that we're correctly predicting everything that we need to. But overall, these metrics are pretty good. And let's look at what we did as a summary. The first thing we did was we collected CVE data and non-CVE data. We then fed these into a neural network to generate an embedding or a matrix. We generated 5 additional features. Because of the sparsity of data, we upsampled our data to 15%. We then trained our GBM model to predict a vulnerability score. Our team has demonstrated the feasibility of vulnerability detection with natural language processing and machine learning, and arguably the methodology is extendable to detect bugs in source code. If you have further questions, please email me at tyler.thatcher@acronisscs.com. that is all we have for today.